Welcome back, everybody. Today we're going to be diving into the world of nanoscale fluid dynamics.
Oh, wow.
It's going to be super interesting. How fluids behave differently at incredibly small scales.
Okay.
And, you sent us this research paper
Right.
titled Thermal Lattice Boltzmann Method for Curved Boundaries in the Transition Regime.
Yeah.
Quite a mouthful, huh?
It is.
Don't worry, we're going to break it down together.
Okay.
So just imagine like a video game
Okay.
where you're simulating fluid flow.
Right.
But instead of like smooth movements,
Yeah.
it's like the fluid is broken down into these tiny particles on a grid.
I see.
And that's kind of what this thermal lattice Boltzmann method, or TLBM, does.
Oh, okay.
And it's especially useful for like figuring out how fluids behave in super small spaces,
Mm-hmm.
like those found in micro and nanotechnology.
Right.
But it gets even trickier when those spaces are curved,
Oh, cool.
which is what this research is exploring.
I see.
We're going to be unpacking some pretty intriguing concepts, too, like
Okay.
knits and layers, slip velocity, and temperature jumps.
Wow.
All things that like defy our everyday experience with fluids.
Yeah. It's like discovering a whole new set of rules
Right.
for how they behave.
Yeah.
It's crazy.
So let's start by setting the stage.
Okay.
This research focuses on the transition regime,
Right.
where the gas flow isn't completely dominated by molecules bouncing off each other
Mm-hmm.
or the walls of their container.
Okay.
It's kind of like this in-between zone,
All right.
where the researchers were looking at how a rarefied gas flows within a circular channel
Okay.
with a constant temperature wall.
Right.
Now, a key player in all of this is the Knudsen layer.
Yes.
Can you help us understand what that is?
So think of a straw that's so thin that air molecules are more likely to hit the straw's walls than each other.
Okay.
That's the Knudsen layer in action.
Wow.
It's this thin region near a surface where those molecule wall collisions just dominate. And it turns out this layer has a huge impact on the overall flow characteristics.
So it's not just about the gas itself,
Right.
but how it interacts with the boundaries of its container,
Yeah,
especially when that container is incredibly small.
exactly.
Okay.
And because this research is focused on a circular channel,
Mm-hmm.
those curved boundaries add another layer of complexity.
Oh, wow.
It's not as simple as just modeling a straight flow.
Right.
Yeah.
So how did the researchers manage to capture all of this complexity?
Well,
Transition regime,
yeah.
the Knudsen layer, and curved boundaries
Right.
in their TLBM model.
They had to get pretty innovative.
Okay.
They essentially took existing approaches for dealing with straight and curved boundaries and combined them in a new way.
Oh, wow.
Like adapting those methods to work together in a 3D environment.
Okay.
If you look at figure 1 in the paper,
Yeah.
it actually gives you a really nice visual representation of this.
I'm looking at it now.
Yeah.
It's pretty intricate.
It is.
But clearly this method works.
Yeah.
Because the researchers were able to uncover some interesting findings
Right.
about slip velocity and temperature jump.
Yes. And these aren't just like
Well,
theoretical curiosity.
Right?
They have real implications for designing things like microfluidic devices.
Oh, wow.
Remember how we talked about the Knudsen layer, where those gas molecules are constantly bouncing off the walls?
Yeah.
Well, that's what leads to slip velocity.
Okay.
The gas actually slips along the surface instead of sticking to it
Oh, wow.
like we'd normally expect.
So like a tiny invisible air hockey table?
Yeah.
The gas is gliding along the surface?
Exactly.
That's wild.
And it gets even wilder
Okay.
because the researchers found that the slippage gets more pronounced
Oh, really?
at higher Knudsen numbers,
Okay.
meaning it's even more significant in those incredibly small spaces.
So you've got this gas like slipping along the walls.
Right.
What about the temperature jump?
Okay. So
What's that all about?
Imagine you touch a hot stove. You feel that immediate temperature difference, right?
Yeah.
Well, something similar happens in the Knudsen layer,
Oh, wow.
but on a microscopic scale,
Okay.
it's a sudden change in temperature between the gas and the wall.
I see.
And just like with slip velocity,
Yeah.
this temperature jump is also amplified at higher Knudsen numbers.
So these phenomena, slip velocity and temperature jump, they're directly tied to what's happening in that Knudsen layer.
Yeah.
Where those molecule wall interactions are so dominant,
Right.
it really makes you realize how different things operate
It does.
at the nanoscale.
Yeah.
And understanding these phenomena is crucial
Right.
for designing micro and nanotechnology.
Absolutely.
Like think about microfluidic chips used in medical diagnostics.
Yeah.
Knowing how the fluid will behave,
Mm-hmm.
especially near the walls of the device, is critical for making sure it functions correctly.
Yeah, for sure.
It's incredible to think that something as seemingly abstract as the Knudsen layer
Right.
can have such tangible consequences.
It is.
And if I understand correctly,
Yeah.
the researchers believe the TLBM method is particularly well suited
Mm-hmm.
for simulating these complex scenarios.
That's right.
So why don't we dive deeper into why they're so enthusiastic about the TLBM method?
Yeah.
It seems like they think it's the key
Mm-hmm.
to unlocking the mysteries of these nanoscale flows.
For sure. Oh, they're definitely right to be enthusiastic.
Okay.
Think about it.
Yeah.
Simulating fluid flow at the nanoscale,
Right.
especially in this transition regime we've been talking about,
Yeah.
it's incredibly challenging.
Yeah, I bet.
Those traditional methods that work so well for larger scale flows
Yeah.
just can't quite capture the nuances of
Yeah.
what's happening when those molecule wall interactions become so important.
So TLBM is like having a specialized tool
Yeah.
for a very specific job.
Exactly.
Kind of like using a fine-tipped brush
Right.
for intricate details
Yeah.
instead of a broad paintbrush for a whole canvas.
That's a great way to put it.
And one of the things that makes TLBM so effective is that it's inherently a particle-based method.
Right.
So instead of assuming the fluid is like a smooth, continuous substance,
Yeah.
it actually simulates the movement of individual particles.
But it does.
It's like zooming in with a microscope and
Exactly.
seeing all those tiny molecules bouncing around.
Yeah, and because it accounts for those individual interactions, it's much better equipped to handle these high Knudsen number flows,
Okay.
where those interactions with the walls are so dominant.
It makes me wonder
Yeah.
if TLBM is so good at capturing these intricate details,
Mm-hmm.
could it also help us figure out how to actually use those weird effects?
That's a great question.
Like slip, velocity, and temperature jump to our advantage.
Absolutely.
Yeah.
Yeah, remember, we're talking about microfluidic devices here,
Right.
incredibly small channels,
Yeah.
often thinner than a human hair.
Wow.
The surface area of those channel walls
Okay.
becomes a major player in how the fluid behaves.
So if we can understand and even predict
Right.
those slip, velocity, and temperature jump effects,
Yeah.
we could design devices that work with those phenomena
Exactly.
instead of fighting against them.
That's the idea.
For example, by taking advantage of slip velocity,
Right.
we could potentially reduce the pressure needed
Yeah.
to push the fluid through the channel,
Exactly.
which could be a big win
Yeah,
for applications where energy efficiency is crucial.
absolutely. Less friction means less energy wasted.
Right.
Trying to force the fluid through those tiny spaces.
Okay, but what about temperature jump?
Yeah,
It seems like that could be a bit trickier to harness, right?
it can be,
Okay.
but it also opens up some fascinating possibilities.
Like what?
Imagine you're designing a microfluidic device
Okay.
for chemical reactions.
Right.
By carefully controlling the temperature
Mm-hmm.
of those channel walls,
Yeah.
you could create localized temperature jumps in the fluid.
Wait, so you're saying we could create like tiny controlled hotspots
Exactly.
within the device?
Yeah, it's like having
Right.
microscopic ovens or refrigerators built right into the chip,
That's why.
allowing you to very precisely control
Yeah.
where and when certain reactions take place.
That's incredible.
Yeah.
We're talking about manipulating fluids and temperatures
Right.
at the nanoscale to
Yeah.
orchestrate chemical reactions.
It's a whole new level of control.
Crazy.
And all of this stems from understanding
Yeah.
the fundamental physics at play in those incredibly small spaces.
Yeah.
So to answer your earlier question,
Okay.
yes, TLBM can not only help us understand those nanoscale effects,
Yeah.
but also potentially harness them
Wow.
to create entirely new functionalities
Okay.
in microfluidic devices.
It's mind-blowing to think that something so small
It is.
can have such a profound impact.
Yeah.
But let's shift gears a bit
Okay.
and talk more about the TLBM method itself.
Right.
The researchers seem very confident that it's the best tool for the job.
Yeah.
Why are they so enthusiastic about its capability?
Well, one of the biggest advantages is its relative simplicity.
Okay.
The basic principles behind TLBM are much easier to grasp and implement compared to some of those other more traditional computational fluid dynamics methods.
Right.
It's like having a more intuitive set of instructions
Okay.
for building your simulation.
So it's more user-friendly in a sense.
You could say that.
That seems counterintuitive.
Yeah.
considering we're talking about such complex phenomena.
It might seem that way.
Yeah.
But remember, we're talking about the underlying principles
Right.
of the method.
Okay.
Of course, when you start dealing with more sophisticated boundary conditions or 3D simulations, things get more complex.
Right.
But compared to some of the alternatives,
Yeah.
TLBM has a lower barrier to entry,
Okay.
which is a huge plus.
I can see how that would encourage more researchers
Right.
to jump in and explore this field. But beyond its simplicity, what else makes TLBM so powerful?
Computational efficiency is another big one.
Okay.
TLBM is inherently parallel, meaning it can be easily implemented
Yeah.
on high-performance computing clusters.
Right.
This allows for much faster and more efficient simulations, even when dealing with the intricate details of those high Knudsen number flows.
So it's like having a powerful engine
Yeah,
that can handle those computationally demanding simulations
exactly.
without breaking a sweat.
And this efficiency becomes even more crucial
Nope.
when you're working with 3D simulations,
Right.
which are often necessary
Yeah.
to capture the full complexity of microfluidic flows.
Okay.
TLBM allows you to tackle those simulations without needing massive amounts of processing power.
And remember, the researchers were particularly excited
Yeah,
about TLBM's ability to handle curved boundaries.
right.
Why is that such a big deal?
Well, think about it.
There's
Most real-world microfluidic devices don't have perfectly straight channels.
Right.
They involve curves, bends,
Mhm.
and all sorts of irregular shapes.
I see.
Being able to accurately represent
Yeah.
those curved boundaries in your simulation
Right.
is crucial for getting reliable results
Okay.
that actually reflect how the device will behave.
So TLBM provides a more realistic and accurate representation
Yeah.
of those complex geometries
Exactly.
compared to other methods that might struggle with those curves.
Traditional methods often have to make approximations
Okay.
when dealing with curved boundaries,
Right.
which can introduce inaccuracies.
I see.
TLBM, on the other hand, handles those curves much more gracefully,
Okay.
leading to more trustworthy results.
It sounds like TLBM is really hitting that sweet spot
It is.
of being both user-friendly and powerful enough
Right.
to handle the challenges of these nanoscale simulations.
Yeah, for sure.
It's amazing to think that we've developed a tool that allows us to explore the world at such a fundamental level. But before we get too carried away singing the praises of TLBM,
Right.
let's shift gears
Okay.
and delve into how this method compares
Hi.
to some of those other approaches the researchers mentioned.
Okay.
So we've spent a lot of time talking about how great this TLBM method is.
Yeah.
But the researchers also made a point of
Right.
comparing it to
Yeah.
other ways of simulating these
Yeah.
kinds of flows.
Exactly.
What makes TLBM
Well,
stand out from the crowd?
it all comes down to the
Okay.
fundamental assumptions behind these different methods.
Right.
So traditional computational fluid dynamics methods,
Okay.
the ones that have been used for decades
Yeah.
to model things like airflow over airplane wings or
Yeah.
water flowing through pipes,
Mhm.
they work incredibly well for those larger scale flows.
Okay.
But when you zoom in to the nanoscale,
Yeah.
especially when those molecule wall interactions become dominant,
Right.
those traditional methods start to break down.
It's kind of like trying to use a map of the United States
Right.
to navigate the streets of a small town.
Exactly.
The level of detail just isn't there.
That's a great analogy.
And one of the biggest reasons
Yeah.
those traditional methods struggle at the nanoscale
Mm-hmm.
is because they rely on what's called the continuum assumption.
Continuum assumption.
Okay, continuum assumption.
Yeah.
Break that down for me.
Okay, so
What does that even mean?
it basically means that we're picturing the fluid
Oh.
as a smooth, continuous substance.
Right.
Kind of like when we imagine water flowing from a faucet.
Okay.
We don't see the individual water molecules
Right.
bouncing around in there.
Yeah.
We just see a smooth, unbroken stream.
Right. We're thinking about the fluid as a whole
Exactly.
rather than all those tiny individual parts.
And for most everyday situations,
Yeah.
that way of thinking about fluids works perfectly fine.
Okay.
But in those tiny, confined spaces we've been talking about,
Right.
especially in that transition regime, where the Knudsen layer is so important,
Yeah.
we can't ignore the fact that fluids are made up of discrete molecules.
So the continuum assumption breaks down
It does.
because the individual molecules are bouncing off the walls so much
Right.
that they're no longer behaving like a smooth, continuous flow.
Exactly.
And that's where TLBM really shines.
Yeah, it does.
Because it simulates the movement of individual particles.
Right.
It naturally accounts for those molecule wall interactions that those traditional methods tend to miss.
It's like the difference between modeling the overall current in a river versus tracking the movement of every single leaf floating on its surface.
So TLBM is giving us a much more granular, almost microscopic view of what's happening in those tiny channels.
Exactly. And because it can capture those individual molecular interactions, it's much better equipped to handle those strange phenomena we discussed earlier. Slip velocity and temperature jump.
It all starts to make sense now. Those effects emerge because of how those individual molecules are bouncing off the walls.
Exact.
And TLBM allows us to see those interactions in action.
That's the beauty of this method.
Yeah.
It gives us a level of detail that was simply unattainable with those older methods.
Yeah.
And that detail is crucial for not only understanding these nanoscale effects, but also potentially harnessing them to create new technologies.
This whole deep dive has been a real eye-opener for me. It's amazing to think that there's this whole other set of rules governing how fluids behave at these incredibly small scales.
Yeah, it's a whole new world down there.
And that we now have the tools to explore those rules.
We do.
And even use them to our advantage.
It's really exciting.
It is. I think it's time for us to wrap up this fascinating journey into the nano world.
It's been a fun one.
We've covered a lot of ground today.
We have.
From the fundamentals of nanoscale fluid dynamics to the intricacies of this powerful TLBM simulation method.
It's a powerful tool.
It is. And hopefully we've inspired you to think about the world in new ways. Recognizing that even at the smallest scales, incredible things are happening.
They really are.
Who knows? Maybe someone listening right now will be inspired to dive deeper into this field.
That would be awesome.
And contribute to the development of new micro and nanotechnologies that will shape the future.
For sure.
If you're interested in exploring further, we definitely encourage you to check out that research paper we discussed today.
There's a ton of great information in there.
There's a whole universe of knowledge waiting to be discovered.
Absolutely.
And until our next deep dive, keep those minds curious.
Be curious.
And stay tuned for more explorations into the fascinating world of science and technology.
Definitely.
Thanks for joining us.
It's been a pleasure.
On this incredible journey.